Okay, so now we are going to study one of the most important equations, the Schrödinger's equation. Okay, so what's Schrödinger's equation? Well, let's go back and look at one of our basic axioms of quantum mechanics, which is the axiom of unitary evolution. It says that a quantum system evolves according to some unitary rotation of the Hilbert space. So U such that U dagger equal to U dagger U equal to the identity. But now you could ask, how do you choose? Who decides what this unitary transformation is? This is going to be. This is the question that Schrödinger's equation answers. It gives us the fundamental quantum equation of motion. Okay, so now before we talk about Schrödinger's equation, we have to talk about a certain observable. It's the energy observable. This plays a very central role in quantum mechanics, and it has its own name. It's called the Hamiltonian of the system. So H is a Hermitian matrix. Its eigenvectors, psi sub I, are the states of the system with definite energy. And its eigenvalues, lambda sub I, are the energies of the corresponding eigenstates. So lambda I is the eigenvalue is the energy of the state psi sub I. So let's do an example. So here's an example. Here's a Hamiltonian H. And now if you work it through, you'll find that it has two eigenvectors, plus and minus, and the corresponding eigenvalues are 2 and minus 3. So we can say that plus is an energy eigenstate of energy 2, and minus is an energy eigenstate of energy minus 3. So what does this mean? It means that if the state of your system psi happens to be plus, and you measure the energy, you'll always see 2. So no matter, if you have many copies of this state psi, and you measure each one, you'll always get the reading that the energy is 2. Similarly, if you had psi equal to minus, and you measured the energy, you'd always see minus 3. But now suppose that psi was equal to 0. Then if you were to measure the energy, half the time you would get a reading of 2, and half the time you would get a reading of minus 3. And the reason for this is that psi is 1 over square root 2 plus minus 1 over square root 2 minus. And so in terms of the eigenstates, the energy eigenstates, when you do a measurement, you see plus with probability half and minus with probability half. And so you see an energy reading of plus 2 with probability half, and an energy reading of minus 3 with probability half. What this means is, if you had 100 particles, each of them prepared in this state 0, and you did an energy measurement on all the 100 particles, then for about 50 of them, you expect to see your measurement result to be 2, and for 50 of them, about 50 of them, you expect a measurement result of minus 3. Okay, so let's do let me just do one more example. So let's say you had your hydrogen atom, and you have your electron in the state 0, 1, etc. So these were your states of definite energy. So now, right, this is a ground state, excited state, etc. These are your energy eigenstates. And so if you were to write out the Hamiltonian of this system, so let's say we had a K-level system of this kind, and you wanted to write out the Hamiltonian of this system, well, what would that Hamiltonian look like? Well, since the basis states are 0, 1, 2, etc., the Hamiltonian would be diagonal in the standard basis, and its entries here would be E0, E1, Ek minus 1, which are the energies of these corresponding states. 0 is off the diagonal. Okay, so now let's get right to the point and say, what is Schrödinger's equation? Well, it's a differential equation. What it tells you is, suppose you're given the state of the system at time t equal to 0, and you're told what the Hamiltonian is of the system, then you can then by solving the Schrödinger's equation, you can figure out what the state of the system is at time t, psi of t. Okay, so there are two constants that appear in this equation. I, of course, is the square root of -1, and h bar is the reduced Planck constant. So h bar is h over 2 pi, where h is Planck's constant. Now, Planck's constant, it plays a central role in quantum mechanics, where the Planck relation E equal to h nu, which relates the energy of a photon to its frequency. So the Planck constant is roughly 6.26 times 10 to the minus 34 joule seconds. H bar is roughly 1.055 times 10 to the minus 34 joule seconds, and it's about 6.58 times 10 to the minus 16 electron volt seconds. So for our purposes, we don't, right now, at least for this lecture, we don't care. The Planck's constant is just some constant. And in fact, we could even assume that we are working in units where h bar equal to 1. Okay, but now, so this thing is a constant, and what Schrödinger's equation says is that the rate of change of the state is h times the state. I'm sure you're thinking, well, differential equations are already challenging enough. But how do you deal with a differential equation with an operator in it? Okay, so it's not so bad if you look at it the right way. So let's look at this the right way. So here's a fact. So let's start in an eigenstate of h. So let's say that psi at time 0, our state at time 0 is phi sub j, where phi sub j is an eigenvector of h with eigenvalue lambda sub j. Okay, so then what we can say is that we can solve Schrödinger's equation, and it has a particularly simple form. What it says is that the state at time t is just e to the minus I lambda jt divided by h bar times the state at time 0, which is this eigenvector of h. Okay, so what is this saying? Well, what it's saying is all that happens, all that Schrödinger's equation is doing to the eigenstate, to the eigenvector of h, is it evolves in time by just changing the phase in front of the eigenvector, in front of the state. And the rate of change of the rate at which the phase precesses is proportional to the eigenvalue, proportional to the energy. Right? So the rate of precession is proportional to the energy. Okay, so if the energy is 0, the phase just does not precess at all. If the energy is high, then this phase precesses very, very quickly. Okay, so let's see how we are going to show this. Well, here's the thing. You see, what happens is, if our state happens to be phi j, then the right-hand side of this equation is just lambda j times phi sub j. And so what Schrödinger's equation is telling us is that the rate of change of the state is proportional to phi j itself. And so what you can conclude from this, so what this is telling us is that if at time t the state is pointing in the direction of phi sub j, then also the change in the state is pointing in the direction of phi sub j. And so we can conclude that even after the change, the state points in the direction of phi sub j, maybe with a different constant in front of it. And so what we can conclude is that the state at all times t is of the form some constant which depends upon t times this eigenstate phi sub j. Okay, so now what we're going to do is you're just going to try to figure out what's this complex number a of t, which depends upon how does a of t evolve with time. And so we substitute this back into Schrödinger's equation. And so we get I h bar d by dt of a of t phi j is equal to h times a of t phi j. And so let's rewrite this. So phi j is, of course, independent of t. And so we can pull it out. So we get I h bar d by dt of a of t times phi of j is equal to a of t times h applied to phi of j is just lambda j phi of j. And so equating these two constants on the two sides, what we see is I h bar d a of t by dt equal to a of t lambda j. And now you might already know how to solve this, or we can just go through it sort of step by step and say, well, the way we are going to solve this is by saying dA of t by a of t equal to lambda sub j when we over h bar, and then I in the denominator is like putting minus I in the numerator, dt. And so solving this, just integrating both sides, we get the natural log of a of t is equal to minus I lambda j over h bar t. And that implies that a of t is equal to e to the minus I lambda j t over h bar. And that's exactly what we set up here. Okay, so what we now know is that we have this precession, that all the eigenstates, they're just, what Schrödinger's equation is telling us is, if you look at the eigenvectors of H, the energy eigenstates, then all they do is they sit there, and the phase in front of them precesses. And how fast does it precess? It depends upon the energy. The higher the energy, the faster it precesses. Okay, so now, of course, in general, psi of 0 is going to be some superposition, sum of alpha j phi sub j over all the eigenstates. And so what Schrödinger's equation tells us by linearity is that the state at time t is going to be sum alpha j e to the I minus I lambda j over j times t over h bar times phi sub j. Okay, what's another way of saying this? Another way of saying this is that there's this, if you look at the state of the system at time 0, so it's alpha naught, alpha 1, alpha k minus 1, then there's this operator you must apply to it. And what's the operator? It's diagonal. It has entries e to the minus I lambda naught t over h bar, e to the minus I lambda k minus 1 t over h bar, and zeros in the off diagonal. And this is equal to psi of t. Okay, the state at time t is given by this operator applied to the state at time 0. So what's this operator? Well, let's call this u, or let's call this u of t. This is the operator that says how the state of the system evolves over a period of time t. Okay, you can check that u of t times u of t dagger is equal to u of t dagger times u of t is the identity, right? Because when you take u of t dagger, you just get e to the I, plus I times this, and then it all multiplies to give you the identity. Now, there's another way of writing this operator. What's usually written is u of t is equal to e to the minus I h t over h bar. Okay, so what do we mean by this when we write something like this? Well, this is just notation. You could think of it as just notation. So when we write that a matrix B is e to the A, let's say is Hermitian, A has eigenvectors phi sub I with eigenvalue lambda sub I, then you could think of this construction when we say B is e to the A, what we are saying is B is a matrix whose eigenvectors are phi sub I, and the corresponding eigenvalues are e to the lambda sub I. So let's do an example. So suppose that we start in the state 0, and our Hamiltonian is x. X, what's x? Well, x is this matrix 0, 1, 1, 0, it's Hermitian, and we want to know what's the state at time t. So how do we even get started on this problem? Well, what we just saw is that we must first discover what the eigenvectors and eigenvalues of H are. So what are the eigenvectors and eigenvalues? Well, X is a matrix we've seen before. It has eigenvectors plus and minus with eigenvalues 1 and minus 1. Okay, so these are the states of definite energy, and the energies are plus 1 and minus 1. So now, what's the next thing we must do? Well, we must write psi of 0 in terms of eigenstates of H. So what are the, how do we write it? Well, it's 1 over square root 2 plus 1 over square root 2 minus. And now we are done. We can just write out what psi of t is. Psi of t is 1 over square root 2 e to the minus I lambda, which is 1 t over h bar, plus 1 over square root 2 e to the minus I times lambda. Lambda is minus 1, so the minuses cancel, so you get I t over h bar minus. Okay, so that's the state of the system at time t. So for example, if you had t equal to pi h bar over 2, then what's the state of our system? Okay, you'd get, well, 1 over square root 2 times e to the h bars will cancel, e to the minus I pi by 2, which is cosine minus pi by 2 plus I sine minus pi by 2, which is minus 1. So you'd get you'd get minus I. So you'd get times minus I times plus. And here you'd get I sine pi by 2, which is I. So you'd get 1 over square root 2 times I times minus. Pulling out the minus I, you'd get plus 1 over square root 2 times plus minus 1 over square root 2 times minus. And what's that? Well, this is just minus I state 1. So in this much time, our state has gone from being 0 to being